Hello everyone, and thank you for joining us for the last Soils Network of Knowledge webinar for 2018. I'd like to introduce Dr. Susan Orwell, who many of you listening will probably know. Susan has worked for New South Wales DPI since 2005 on a range of soil health projects. She's currently the leader of Soil South in the soils unit, but still has research interests in management strategies to increase soil carbon, covering topics such as carbon fractionation, subsoil carbon sequestration, and the management of pastures to increase soil organic matter, some of which is covered in her presentation today, which is looking at whether there's more value in accumulating soil carbon or using soil organic matter to gain agronomic value.
Okay, thanks Abby, and good morning everyone. I'd like to start this presentation by acknowledging the co-author, who many of you would know, Dr. Mark Conyers, for this presentation. And this presentation Mark and I put together because we were constantly being asked the question, many of you would know soil carbon seen as the silver bullet for many situations, and people would see pasture phases as a way to not only build soil carbon but also use nitrogen for the following cropping phase. And this presentation is aimed at showing people that often when we think about carbon accumulating, it's not just keeping carbon in the soil, but it's actually the dynamic nature of organic matter cycling that's important for agriculture rather than just a continual increase. So to begin with, let's think about mixed farming systems of southeastern Australia. The traditional rotations relied upon the build-up of organic matter during the pasture phase and the mineralisation of nitrogen during the cropping phase. So today I'm going to present some historic and some more recent data on why it's not necessarily that straightforward silver bullet for carbon sequestration, and often the value of soil organic matters in it being dynamic, not simply just accumulating. If we start with some fundamentals, we know that soil represents a significant pool of carbon, and for this reason, it's been seen as an important tool to mitigate climate change. So when we compare it to the amount of carbon in the atmosphere and in terrestrial biomass, so in vegetation, we know that soil stores more than both of these combined. So it's a really important store of carbon that could be otherwise warming the atmosphere. But when we talk about carbon, what we're really talking about in farming systems is soil organic matter, and carbon's the component that we measure. So soil organic matter is approximately 58% carbon by weight, and that means that the other 42%-ish is made up of other nutrients. And so we've got things like oxygen and hydrogen, which come from water and the atmosphere, and then we've got some of the other nutrients that we're interested in because they support our agricultural systems. So things like nitrogen, phosphorus, sulfur, and a range of other nutrients and trace elements. Really importantly, what carbon in the soil does is provide energy for microorganisms to mineralise nutrients, and that's a really important component of phase farming systems. Soil organic matter, it can be things like the roots that we can see, it can be microbes that we can't see, but when microbes turn the soil dark, that's what we refer to as humus in the soil, so which gives the soil its dark colour, and also charcoal. And we know that all plants are able to take up nitrogen from soil in the form of ammonium or nitrate. And when we add these together, it's known as the soil nitrogen pool. Legumes are really important because of the little nitrogen fixing kind of factories that they have in their nodules, which contain rhizobia. So when we think about the sacred benefits of pasture rotations, we know that when we have a pasture rotation in a cropping system, we fix nitrogen and we build soil carbon, and this is in the form of soil organic matter. Pastures are also really important for improving soil structure through fibrous roots and through the root exudates, which help stick soil particles together and make soil structure more stable. Soil organic matter is really important in these systems, and it builds up through pasture rotations, and it helps stabilise and enhance the retention of soil nutrients as well as soil moisture. And more recently, pasture phases have been focused on for their ability to sequester carbon. But we also know that good crops need lots of nitrogen, and this comes from either the soil pool and or fertiliser. So it's inevitable that as soil nitrogen mineralises, we get a decline in soil carbon. Then we have the dilemma. And this dilemma revolves around, since the carbon to nitrogen ratios vary from only about 10:1 to 14:1 in the surface soil, and just keeping in mind that if we use wheat stubble as an example, the carbon to nitrogen ratio of wheat stubble ranges from about 60 to 100:1. The provision of soil nitrogen comes with a loss of soil carbon. So what I mean by that is, as microbes decompose organic matter, they either take nitrogen from the residues, or they'll take it from that more stable form of organic matter in the soil to decompose that organic matter. So the carbon respires. You get a concentration to some extent of nutrients in terms of building up that microbial or that humic fraction of soil, but in fact, we've actually taken nitrogen from what could be used for a plant. So what's the solution? So perhaps we can't sequester carbon and have cheap nitrogen as well. And for many of us, we see that build-up of carbon and nitrogen during the pasture phase as having a really important agronomic value for the following crop. I think we can kind of counter this. So we know that we've got the carbon and nitrogen build up during the pasture phase. What we can try and do is avoid a net rundown of soil organic matter, carbon and nitrogen, over time. So we try and build it high enough during the pasture phase, knowing that it's going to run down when we go back into cropping, but make sure when it runs down, it's still at a higher level than it began with. So I don't want you to switch off your computers now, but that's the main message and the key processes that this presentation is all about. What I want to do now is look at some examples of how we've seen this over time in our long-term trials. If we start with the first trial, which is called the Conrot trial, which it's named after Peter Con, a researcher from New South Wales DPI based at the Wagga Wagga Ag Institute. And it was an 18-year trial based at the Ag Institute on a Canada soil. And the site had a low starting carbon level, and this is important to note because this is where we see the maximum potential for carbon sequestration. Basically, if the soil is less saturated with carbon, the bigger the sponge is or the gap is to fill. There was 3 cropping intensities, so we looked at long-term or short-term rotations, and those rotations consisted of wheat and lupins and a subclover rye pasture. Fertiliser was applied at about 12 kilos of phosphorus per hectare per year, and cropping was carried out during the kind of traditional practice of multiple passes with the stubble burnt. So if we have a look at some of the results from this trial, so this is an aggregated snapshot, and we're looking at results over the top 30 centimetres of soil here, and I just want to explain this table. So where I've got, if we take, for example, the 50% pasture, 50% wheat example, and as I said, this is run over multiple years, that could mean pasture, wheat, or it could be pasture, 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 wheat, wheat, wheat. So we've aggregated the results here. And that's the first 2 columns. If we look at the far right-hand column, which is, I guess, the key message of this trial that I want to show you, is that the greater the presence of the pasture in rotation, so the higher the number in the green column, the higher the annual carbon accumulation. So we can see that the more pasture years you have in rotation, or the greater proportion that pastures take up of that total rotation, the more carbon that accumulates over time. So we're not just looking at a snapshot, we're looking at over the entire trial. And that was up to 0.5 tonne on average per hectare per year of carbon sequestered. Remember, it started from a low baseline. And that's an important and interesting result. If we then move on to thinking about what the nitrogen did, because remember I said carbon builds up and nitrogen builds up, and then you have this rundown period. So the graph that I've got on the screen at the moment, it's meant to be blanked out because I just want to describe it before I show you the detail. On the x-axis along the bottom, we've got some examples of the rotation treatment. So W refers to wheat and P goes back to the pasture. On the y-axis, where the 0 is, everything above the 0 means that it was an accumulation of nitrogen during that rotation. Everything below the 0 means that it was a rundown, and we're looking at nitrogen in the top 10 centimetres. Now the wheat is the open columns, and the pasture is the closed columns, and we've got the standard errors there as well. So what we can see across the rotations that during the pasture phase, we've got columns which are above the line, which means it's accumulating nitrogen. And during the cropping phase, we've got the open bars, the wheat bars, are below the line. So we've got a build-up of soil organic matter, which includes nitrogen. Then when we return to the cropping phase, we run down that nitrogen, which is getting the agronomic value out of our pasture phase. Let's move on to the next trial, the SatWaggle trial. And SatWaggle stands for the Sustainable Agriculture Through Wheat and Grain Legumes. And this was another trial based at the Wagga Wagga, run through the Wagga Wagga Ag Institute. But this time we had a reasonably high initial soil organic carbon to start with. And again, we'll be looking at soil carbon stocks from the 0 to 30 centimetre depth. Now here what we had were stubble, tillage and grazing contrasts. There were 3 rotations, so wheat and lupins, wheat and subclover, and continuous wheat. There were 2 stubble management treatments, so it was either retained or it was burnt. And there were 2 tillage treatments, so no-till or conventionally cultivated. So I've given an example there that's 3 cultivations using offset tandem discs in the earlier days, and then that moved into scarifiers in the later days. Now, the plots were fertilised, and some were grazed and some were mulched. And what we've got now when we look at this table, so it's looking at carbon change to 30 centimetres. If we just focus on the different colours that you can see there, the 3 different colours are grouping the treatments in accordance with the rotation. So we've got lupin wheats in the yellow, and then the kind of burnt orange colour is the continuous wheat with and without nitrogen. And then the green one down the bottom is our pasture rotation, so where it's subclover wheat. The next column along is the stubble management, followed by the tillage management. So if we zoom across to the far right-hand column, we can see that there's a whole lot of negative numbers, and they kind of become larger the more cropping intensity, I guess, is undertaken, so under continuous cultivation and continuous cropping. If we see where the only positive number is, it's where we had a pasture in rotation, so where we were sequestering about 0.25 tonnes of carbon per hectare per year over this long-term trial. If we then go to look at, again, the pattern of nitrogen accumulation and turnover over time, here we have on the x-axis, so we're going to be looking at 9 treatments, just a snapshot of this trial. And on the x-axis, we've got time, so from when the trial first started to 2000. On the y-axis, we've got organic carbon in tonnes per hectare, ranging from 5 to 25 tonnes per hectare. Now I've just revealed that you can see we're going to have different treatments. So remembering that LW is lupin wheat, stubble retained, if we look at treatment 1 and no-till. The main thing to see is in the bottom column, we've got our pasture rotations, so treatment 7, 8 and 9, and everything else was a crop in rotation. Now you'll see why I didn't want to show you this slide as is, because it looks a little bit confusing. But now I've introduced you to what the graph's showing. What we really want to see is the trends. So first of all, so the circles are carbon and the triangles are nitrogen. First of all, let's look at the carbon and nitrogen trends together in general. So across most of those treatments, you can see that they stick together, because remember, soil organic matter is a certain amount of carbon and a certain amount of nitrogen in general once it gets to that soil organic matter classification. So we can see that those lines kind of run together almost in parallel. That's the first thing to note. The second thing to note is for the first 2 rows of columns where we've got the wheat or lupins wheat, you can see that in general, those fitted lines, so the modelled trends, are all trending down. So over time, we've got that decline in carbon, and that was reflected in the previous slide where we had the negative values. Now, the third thing to note here is that the only time you see either those being quite stable or increasing, those trends in both carbon and nitrogen, is in the bottom column. So we're treatments 7, 8 and 9 in this figure, where we've got pasture in the rotation. So getting really repetitive, I see, but hopefully you'll see that if you build up soil organic matter, you build up carbon and nitrogen, but when you go back into that cropping phase, then you'll get that rundown. So let's look at that rundown. Now we've got those lines are modeled values, and what you can do with those trends out of that graph is have a look at how much rundown or increase we actually had. So just confirming what we saw in the graph, we can see we had a rundown in carbon, which is the second column along, under all the treatments where you had a crop in you just had a lupin or wheat crop or a wheat crop, but where we've got the positive value, which is the second from the bottom, 185 kilos of carbon per hectare per year to 30 centimetres, was where we had our pasture in rotation. Now, the other reason I wanted to show you this, if you look at where the -4 is, so the bottom row there, that was a pasture in rotation, but it was continually cultivated. So the difference there is where we've got, I guess, we're breaking up the soil structure and you're facilitating a respiration of some of that organic matter, so microbial activity, and organic matter turnover there. Similarly, if we look at the nitrogen rundown, you can see the similar pattern because, again, we saw that those lines ran in parallel a few slides earlier to one another. Now let's move to the master trial. And the master trial was the trial it stands for Managing Acidic Soils Through Efficient Rotations. And again, we're looking at analysis of carbon and nitrogen to 30 centimetres. And this trial was conducted at Book on an acidic soda soil. For this trial, what we had is, previous to the trial being sown, it was annual pastures, subclover, some volunteer annual grass and weeds and things, and then the site was limed. And what we're looking at is the influence of an annual versus a perennial pasture, and liming that annual pasture or liming that perennial pasture. So, and for the context of this presentation, we're looking at the influence on carbon sequestration and nitrogen buildup. Now, these are the results for, as I said, it's a long-term trial again. So we've averaged these across the trial. The fluorescent green looks at the pasture treatments, either perennial pastures, so the perennial pastures were Flaris and Cocksfoot, or the annual pastures, which were just annual rye and subclover, with and without lime. So the first two are without lime, the second two are with lime. So instead now of looking at the influence of cropping rotations going back into these systems, we're just seeing whether or not the perenniality of the pasture and liming that pasture makes a difference. And we can see just having a pasture in this soil has increased carbon sequestration by roughly about 0.5 tonne of carbon per hectare per year. If the next obvious question is whether or not lime had an influence. So there was no significant difference in that liming treatment on carbon sequestration, other than if you look where the annual pastures were limed. And what happens when you lime the soil isn't necessarily that you just get liming the soil produces carbon dioxide just from the lime reaction in soil. But what we're seeing here is we've altered the soil environment for soil microbes so they can facilitate a more ready turnover of organic matter, and that's limited some of that carbon sequestration value in the annual pasture. With perennial pastures, where you've got a greater soil stability and soil structure, and that organic matter is being wrapped up nice and tightly within soil aggregates, there's less of a penalty, and in fact you'll get in that case a higher rate of carbon sequestration per year. So if we look at that trend over time, because they were the values per year, but we can see where that increase occurred. On this graph here, on the x-axis, we have our time going from 1990 to 2006. On the y-axis, we've got our soil carbon stocks in tonnes of carbon per hectare to 30 centimetres. Now I've revealed the graph. So what we have here are the circles are the annual pastures, the triangles are the perennial pastures, and the closed circles are without lime, or the closed symbols are without lime, and the open symbols are with lime. So we can see that soil carbon sequestration isn't always a set amount per year, so it kind of bounces around a fair bit. We can see where the annual pasture wasn't limed. It took a while for that annual pasture to start to build up carbon levels. But by the end, so after the 16 years that this graph covers, they were roughly at about the same levels. The last trial that I want to briefly introduce you to for similar purposes is our Evercrop Carbon Plus trial. So this particular trial was conducted at Youre Creek in southern New South Wales on a red Candace soil. And what we were looking at here was whether or not the type of pasture in the pasture phase influenced carbon sequestration to depth. So we were looking at carbon sequestration in this trial down to 1.5 metres. And we're also looking at whether or not a well-fertilised, continuously cropped site could still maintain or increase carbon levels. We had 3 different sowing years for this trial, so 2008, 9 and 10, and the pasture types are listed there. So they're common pasture mixes, so 3 years of Phalaris sub, Coxfoot sub, Lucerne sub, Chicory sub, and we were comparing that to a continuously cropped site. And just important to note that the continuous crop was also fertilised. So if we have a look at some of these results, so I've presented the results here for 2013 and 2014. And remember, we had 3 sowing dates, so either 2008, 9 or 10, and each of the trials had 3 years of pasture. So depending on the sowing year, the years in crop will differ, and that's what I've tried to indicate in the far right-hand corner. So when we look at the 2010 results, that's after 2 years of crop, or for the continuously cropped site, 6 years of crop. For 2009 zone trials, that was after 3 years of crop. So they've gone 3 years of pasture, 3 years of crop. Now I've revealed what some of those results are. So I've just plotted here the trial plot data. The reason I wanted you to see this was, apart from the fact it looks like a shot up road sign out of Clover or something, is that you get variability within the plots, and this is just natural variability, and you'd see it at an even greater extent at the paddock scale. If we look at, and in particular, you can see for the 2009 Coxfoot site when we sampled in 2014, there's a huge carbon stock value, which is quite different to the rest. So I should have pointed out, on the x-axis, we've got our carbon stocks in tonnes per hectare there. What we can see, though, if we just look at pastures versus continuous crop, for carbon, you can see that it's quite comparable. And this study actually showed that if you fertilise a crop, even if it's continuously cropped and you don't have the pasture phase in there, you can still maintain carbon levels or even increase them if you get the rainfall. Because what we were doing is we weren't relying on the organic matter from the pasture phase, we're putting on it in a bagged form. But for the rotations which had a pasture in it, we can see that they had comparable carbon levels, even though we weren't applying nitrogen to the crop. So if we look at those trends now over time, again, we've got the different sowing dates in this graph here. We've got our depths along the x-axis. So I always need to look at this graph with my head on the side, because what we are looking at is the depth descending with carbon concentration on the y-axis now. And you can see that if you just eyeball across all of the treatments, and these are the modelled mean values. So it's the data that you saw in the previous slide, but it's looking at it with depth, so not looking at carbon stocks, but looking at carbon concentration. There's no kind of screaming winners out of that, because we were fertilising the crop. So the crop was getting its nutrients from the bag, not from organic matter. Also importantly, though, with those with the crops which had been sown into where you'd had a perennial pasture, they were comparable carbon levels. We can look at a similar graph now for nitrogen. So this is looking at total nitrogen concentration. The difference you can see here is that the red line is 2014 and the black line is 2013. So with that extra year, you'll see you've got an increase in the amount of nitrogen in those systems, and in particular in the systems which had pasture. So the red line is above the black line, which means it's got a higher level of nitrogen concentration, which means that you've mineralised some of the nitrogen throughout the profile. That's important. So it's just not just in the top. In fact, it actually happens more readily deeper down in the profile. So let's think about our take-home messages. First of all, carbon sequestration is actually slow and sometimes screamingly unspectacular in some of our soils, and that's just the nature of the beast. Really importantly, we use our organic matter for the agronomic value. It is still absolutely essential to maintain or build organic matter in soils for a whole range of reasons. Where the soil is already at over 1% soil organic carbon, our maximum carbon sequestration rates are sometimes 0. So perhaps we can't, because of this idea of saturation, and also, so that's saturation of the soil, and also what happens is you get this kind of maximum biophysical limitation of what you can potentially produce in that area. But the more biomass you can produce, however you do that, the more carbon or organic matter that goes into the soil to potentially, in the end, be stabilised as soil organic carbon. So I guess the other thing to highlight is that productivity and environmental benefits of soil organic matter accumulation are sacred. So we know that it's really important for production, but it's also really important for enhancing the natural resource base of soils. But for both of these components, soil fertility as well as soil structure, we rely on that soil organic matter pool as being dynamic and continuously accumulating. So you don't just want it to get in the soil and stay there forever. We want to put it in the soil, have it turn over and be constantly replacing it. And that's where we can get to tweaking the system. In relation to the pasture phase and the cropping phase, you can see that there's a bit of a choice. If you were trading the carbon, what you'd need to do is apply nitrogen from the bag, whether it's a mineral fertilizer or an organic fertilizer, when you go back into the cropping system, into the cropping phase, sorry. Otherwise, you're using the carbon or the nitrogen from the soil organic matter and you'll have a loss of carbon. So the agronomic value in soil organic matter is through that soil organic matter cycling, and that may result in a declining carbon when you go back into the cropping phase. The important part is then to go back into another pasture phase to maintain that soil organic matter level. I would also, so this is my last slide, so thank you all very much, but I would also urge you to participate. There's a global survey that's out at the moment, and if you type the term CIRCASA, which is the sounds like it's from the Lion King, but CIRCASA into your search engine, there's quite a comprehensive survey that the global soil carbon community is undertaking at the moment to see what farmers are doing to sequester carbon in soil and what the barriers to carbon sequestration practices might actually be. It's a long survey and it's got a global view. So you answer it for your region, but just be a little bit tolerant and patient because it can be tedious in places.
Okay, so everyone, thank you very much, Susan. That's fantastic. I'm sure there's lots of questions. So as I said at the beginning, now we have a chance to ask questions of Susan or to pass comment or whatever. I know that Luke has a question.
Thanks, Abby, and thanks, Susan. So, Susan, my question's pretty simple. If my aim was to build up soil carbon, do I need to, be adding fertiliser to do that? If that's my aim, or to have more stable soil carbon?
Yeah, that's a really good question. Thanks, Luke. Look, if your aim is to build soil carbon, the best way to do that is to make sure that you're maximising biomass production. And the best thing about that is that relates to what we want to do in terms of boosting productivity in agricultural systems. In terms of stable soil carbon, what Clive Kirkby's research showed is that to build up that microbial debris or the humic fraction, the really stable part of soil organic matter, it requires nutrients. So nutrients, doesn't matter if it comes from an organic source or a mineral source, but microbes need those nutrients to stabilise carbon in soil. So as I said before, in the surface soil, our carbon to nitrogen ratios are about 10 to 1 or 14 to 1. If we look at fungus, fungus in the soil has a carbon to nitrogen ratio, I think it's between 8 to 25 to 1, and bacteria is around about 5 to 1. what that tells us is that fungus and bacteria are highly concentrated in nutrients. So they need nutrients to stabilise carbon, and they'll take that regardless of what we do. So they'll either take it competing with plants, or they'll take it and supply it to plants. So that's where Clive talks about you either fertilise the plants, or you could think about fertilising for the soil, so looking at that microbial community in the soil as well, and that would create more stable carbon.
Okay, thank you for that, and thanks for the question, Luke. I do notice that Phil Cranny has his hand up.
Susan, just wondering if there is an opportunity for croppers after a really high yield season to incorporate their stubble and add some fertiliser with that stubble and lime, and possibly that might be a way of stabilising or increasing soil organic matter.
Yep, no, most definitely. So you would stabilise soil organic matter, but if you did a soil test, you might not see an increase in soil organic matter, because when we test for soil carbon, it includes all the fractions, and while humus is the biggest fraction of carbon in the soil, there's a bit of a lag period. So what we build up most readily is the more particulate or labile fraction. So you'd actually, in incorporating stubble and adding nutrients and lime, you'd kind of get a big boom in the microbial community and microbial activity. You'd actually get an increase in soil respiration. So while your stable carbon might accumulate, your overall carbon might decline a little bit, because you're kind of churning through that particulate organic matter. And the other risk would be when those nutrients become available to plants, there might be a bit of a delay.
Excellent, thank you.
Okay, thanks for the question. Narrowly, Brendan also has a good question, and she's asked about, what's the preferred or optimal length of the pasture phase for optimising that build-up of soil carbon?
Yeah, that's a really good question, and I got asked this at the Institute Agronomy conference as well, and I didn't have an answer then, and I don't now, because we don't really look at long-term trials anymore for this kind of flexibility under modern farming systems. So if we look back at those examples that I've presented today, it just shows that the presence of a pasture phase is what's important. I think it's more the length of the pasture phase and then the length of the cropping phase. So if you went pasture crop, then perhaps you'd kind of meet that balance of organic matter supply and nitrogen supply and turnover, and then build up again. If you just went 2 years of pasture and then had 6 years of cropping, you'd kind of go below that line that I've kind of indicated on the slide that's up at the moment. So narrowly, it's a really good question, and I wish I had an answer. It would be soil type dependent and also regional dependent as well. When you've got years like this, when there's hardly any rain, then that's going to influence it as well. And that's the benefit of long-term trials, kind of capturing that climate variability.
Yeah, it's tricky, isn't it? I think Jason last month made a bit of a plug for long-term trials as well for the work that he's involved in. Okay, we've got some more questions, which is great. Amanda Chappelle has said, what effect do you think the drought conditions will have on soil organic carbon values in the next few years? So you sort of touched on that, but do you want to elaborate?
Yeah, most definitely. So I've got some trials, some sampling sites that I monitored down on the Monero, and I started those trials in 2009, which was kind of in the last year or two of the Millennium Drought. Then I've monitored them in 2009, 12, 15, and I've just sampled them again. And so we've gone out of a drought, had the best couple of years, and then we've had an okay year, and now we're back into really muted conditions. And what you see without any change in management, in particular, or any nutrients going into the soil, just with that climate variability, huge fluctuations in carbon. And when I say huge, we're talking going from drought to looking at 3 tons of carbon being sequestered per hectare per year, just off the charts. And then when it gets to dry conditions again, if it builds up that quickly, it runs down even quicker. So it's this kind of boom and bust of particulate organic carbon. in cropping systems, if there's tillage involved as well, that boom and bust happens even quicker, because what happens is you get that in good years build up of particulate organic matter. But that takes a while to be stabilised. It's stabilised either in the humic form or wrapped up nice and tight in a soil aggregate. If you then cultivate, what can happen is you expose that really vulnerable form of carbon, and then it's lost really quickly.
Muted.
So now it's important to look at carbon levels all the time, in my opinion. Totally biased, put that out there. But now you'd be expecting to see lower levels, particularly of that more labile fraction of carbon.
Unmuted.
Okay, thank you. And Phil Cranley has another good question. He said it looks like a subclover break is underutilised in modern farming systems as a way of stabilising soil carbon. So do you have any hints on how to encourage producers to adopt this method?
No. I don't know. Like, I agree, Phil. And I think there's a few things that we need to align in terms of addressing soil fertility, soil acidity, to get everything in line, not only for organic matter accumulation and kind of that, because really when we're talking about organic matter accumulation, we're talking about enhancing soil functions, so that microbial health of soil. And that
Muted.
does, and not a, yes, it can be a silver bullet for carbon sequestration, but what it does is helps that system grow more and also stabilise more, both in terms of plant material and soil organic matter. For pasture phases, I think it's a no-brainer in terms of resilience of the farming systems, but I also see that kind of complexity of moving in and out of, or shifting your livestock to cropping ratios seems to intimidate farmers as well. So I don't know what the answer is to that one either, but I think it's certainly shows that pasture phases are really important, are kind of an essential component of cropping rotations for that structural and for the carbon and nitrogen component as well.
Unmuted.
I guess also it would be, you kind of touched on it, Susan, would be asking producers what they see as the barriers for them in moving to that kind of a system, because presumably some people practice that lay farming more widely in the past.
Yeah, that's right. And yeah, no, that's exactly right. And I think what we need to do is look at, and the kind of image that I've got on the screen at the moment is looking at kind of shifting, not only for soil carbon, but just in general, kind of maximising the rotation. That's why Nerali's question was so good. What is the ideal pasture length? And I gave a rubbish answer because I don't know. But kind of lifting that new upper limit so that we're not kind of defined by this really fragile bouncing around of soil organic matter, but we're defined now by the next big thing, clay content, which we can't kind of change. So.
And I guess what would you say then too, because I think I'm going back to a point I think also that Jason touched on last month, that about, you know, taking the opportunity to monitor yourself if you don't know what's there. So in terms of referring to Nerali's question, and that there are all those intricacies and factors that affect that, whether, you know, doing your own sort of monitoring to find out what your best options are is a good thing to do.
Definitely. And I mean, most of the soil analysis providers at the moment also offer carbon for not much more once you're getting your phosphorus and sulfur and other things, and pH tested, which is really important to monitor. And these days, as long as you've got a good sampling strategy, we know that once it gets to the lab, it's a really solid reflection of what the level actually is. It's just making sure that you've got a representative soil sample for when it gets to the lab. Otherwise, you might see that bouncing around in values which more reflect, I guess, variability within the paddock than variability within the actual kind of year or management treatment.
Yeah, and he talked about that too, and he said, I can't remember the number. I think he said about 25. So he talked a bit at length about that, whether your sample size was a metre by a metre or a hectare by a hectare. You had to have a minimum of 25 samples to take out all that variability that you've just talked about.
Yeah, so Mark and I just released a paper last week which was looking at carbon and nitrogen variability to 1.2 metres, and it had a range of other great collaborators, which I'd also like to acknowledge in this presentation, from the Wagga Wagga Ag Institute as well, who do a lot of this work with us. And it basically showed that it all depends on what amount of error that you're willing to accept, but certainly around that traditional recommendation of 20 to 25 cores will give you a good estimation of the mean carbon or nitrogen value to depth as well, which is really important.
Unmuted.
Could be ridiculous and sample more, but
which
the
is what
benefit you
Jason
get
said
from that-
too. Yeah, he said there's a point at which it's not worth it. Yeah.
Yeah, that's right. So
Oh, okay. Phil's just posted another comment. He says, regarding the drought issue, there may be a temptation to reduce traditional sowing rates of nitrogen application next autumn, given the low mineralisation levels over the past growing season. Any comments? Good question.
yeah, that is a good question. And this is where you need to think about, and this is, I'm sure this is what you're getting at, Phil, just preceding years as well. If you haven't had that build up of organic matter and
Muted.
moisture and temperature has been limiting mineralisation, microbial activity in the soil, then certainly you can't expect that it's going to be there for the next year. In saying that, with some of our nutrients, if it hasn't been used, then it's still there. So you wouldn't apply something like P if you haven't been having successive good years of cropping and haven't had that crop removal. But things do slow down, and if you've got less organic matter that's gone into the system because you've had a few years of below average yields, then we know that nitrogen isn't going to be readily available in that system. So that's not to say that once a bit of moisture gets in there, the bugs won't get nitrogen from that soil pool, but the timing's not always right. The amount isn't always right. So it's a lot more unreliable in that sense, rather than when we've had successive good years and we know that we've had that good build-up of nitrogen.
Okay, I think that's it. I would like to thank Susan for ducking out of her meeting this morning to present the final SNOC webinar for this year, and also thank you all for your attendance, and look out for your invitations next year. So yeah, thank you very much, Susan, and I hope everyone has a lovely Christmas, and see you in the new year.